Okay, guys, continuing on with 3.3, I want to start off by reading the rational zeros theorem. And this is in your book. This is page 328. It says if P over Q is a rational number written in lowest terms, and if P over Q is a zero of F, a polynomial function with integer coefficients, then P is a factor of the constant term and Q is a factor of the leading coefficient. Just reading that over, it's kind of hard to tell what it means the first time you see it. So what I'm going to do is I'm going to show you through example. Okay. So I'm not going to worry too much about, what's P and what's Q. So what this says is list all possible rational zeros, then find the rational zeros, and finally factor the polynomial into a multiple of linear factors. So the difference here is they're not giving me like a K value that represents a zero or a linear factor to start with, okay? So I have to figure out, well, how the heck do I do this then? That's where the rational zeros theorem comes in, okay? So by the rational zeros theorem, all it's saying is, as long as all of my coefficients here are integers, which they are, it says any rational zero, so any real zeros that aren't irrational, are of the form any factors of the constant term over any factors of the leading coefficient. That's your P and Q, okay? So what this says is it's factors of -10 over, in this case, factors of 1. So if I list them out, it's plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. That's the factors of -10. You could have positive 10 and -1, -10 and positive 1, positive 5, -2, positive 2, -5, and all those different combinations. And on the bottom, this is nice. This is just plus or minus 1. So when your bottom is just plus or minus 1, it just really breaks down to whatever's on top. So that's kind of the nice thing when you just have a single 1 out here. So right here, these are all of our possible rational zeros. And the question is, well, how do we figure out which one of these works? Okay. Well, what we're going to do is we're going to just test them. Okay. So sometimes this can take a little while, hopefully not. So I'm going to test if positive 1 is a 0 first. So I'm going to use positive 1 as my 0. So here's what I'm checking. If 1 is a 0, which also means x minus 1 is a factor. That's what I'm checking right now. And I'm just doing the synthetic division here. -13, -10. And I'm going to see if I get a remainder of 0, then I know 1 is a 0. If not, then I'm going to move on to the next number. So 1, 1, -1, -1, -14, -14, -24. That doesn't work. Next thing I'll try is -1. So I check positive 1, now I'll check -1. I usually just kind of move to the right. So let's try -1. 1, -2, -13, -10. 1, -1, -3, 3, -10, 10, 0. So what does the 0 tell me? The fact that I got the remainder of 0 tells me that -1 is a 0. And since -1 is a 0, x plus 1 is a factor. So now what I'm going to do is I'm going to write this out. So I was using P of x. I just use it because polynomial. So P of x, which I know I can write this way. Well, I can write in factored form, or at least partially fully factored form, with x plus 1. And the next thing I need is just the leftover. So that's just going to be x squared minus 3x minus 10. From there, you can factor this the old-fashioned way. So that's x plus 1, x minus 5 plus 2, fully factored. So you're good from right there.